So we were doing that S phi is equal to T phi and S dash phi is equal to T dash phi. This we have, correct? Now we calculate SS dash phi. What is SS dash phi? It is S phi into S dash phi. We can write this or not? Why? Why we have written like this? Because see, phi is what? Phi is homomorphism given. It is given that let phi from S to T be a morphism. So we can write like this: S phi into S dash phi. Correct? Now you put the value S phi is equal to T phi and S dash phi is equal to T dash phi. Correct? Now again this can be written as TT dash phi. So we have proved that SS dash phi is equal to TT dash phi. So SS dash phi is equal to TT dash phi. It implies what? It implies that SS dash comma TT dash belongs to kernel phi. Correct? So we have proved that SS dash comma TT dash belongs to kernel phi. It means that phi is compatible. Kernel phi is what? Compatible. And we have already proved that it is equivalence relations. So compatible equivalence relation is what? Congruence. So kernel phi is congruence. You can write it implies that kernel phi is compatible. So kernel phi is congruence on S. So we have proved that kernel phi is congruence relation on semigroup S. So remember that kernel phi is a congruence relation on a semigroup S. Correct? Not always. Situation should be like this, that phi from S to T is a morphism, then kernel phi is a congruence on a semigroup S. Otherwise, in general, we can say that kernel phi is equivalence relation. Correct? So now what we have to prove more? We have to prove there exists a monomorphism from alpha from S from kernel phi to T such that image alpha is equal to image phi and this diagram commutes. C to prove alpha from S by kernel phi. See, kernel phi is what? We have proved that it is equivalence. So we can think about the quotient semigroup as I already told you that when rho is a congruence, correct? Rho is a congruence, then S by rho is what? Quotient semigroup. S by rho forms quotient semigroup. So we have proved kernel phi is a congruence. So S by kernel phi, we can think about that it forms a quotient semigroup. S by kernel phi, correct? So first we have to define a mapping, and after defining mapping, we have to prove that it is a homomorphism as well as 1-1. So first we define. So we define a map. Let's see how we define a map. We define a map from define a map alpha from S by kernel phi to T by A kernel phi alpha is equal to A phi. Correct. We define a map like this. Without loss, we have to check that this map is well defined or not. We have defined a map like this. We will check that this map is well defined or not. So to check map is well defined, let A kernel phi is equal to B kernel phi. It implies that A comma B belongs to kernel phi, because kernel phi is a relation. So A comma B goes in kernel phi. So A comma B goes in kernel phi. It means what? It means that A phi is equal to B phi. So we have taken A kernel phi is equal to B kernel phi, and we have proved that A phi is equal to B phi. It means what? This map is well defined. And also this map is 1-1 because we can go in a reverse way. Because if you take A phi is equal to B phi, it means that A comma B belongs to kernel phi. A comma B belongs to kernel phi, it means that A kernel phi is equal to B phi. So by this we can say that alpha is well defined and 1 1. Well defined map and also 1 1 map. We can say both because we can go from up to down and down to up. So alpha is a well-defined map, 1 1 map. It's okay. Now we have to prove that it is a morphism. Morphism in semigroup means homomorphism. So we have to prove it is homomorphism. To prove it is homomorphism, we have to take two elements. You take two elements for any A kernel phi, B kernel phi belongs to S by kernel phi. So A kernel phi into B kernel phi. We have taken two elements here, and now we are operating on alpha. So A kernel phi into B kernel phi. Kernel phi is what congruence. So it can be written as A B kernel phi alpha. Now A B kernel phi, what it can be written as? See, kernel phi is what congruence. So A kernel phi into B kernel phi can always be written as like A B kernel phi. This we have, correct? So now, how we defined it? How we define that? We have defined this as AB phi, as we have defined earlier, mapping like this. Now AB phi can be written as I'm writing here, that is equal to AB phi means A phi into B phi, correct? Now you write in the place of A phi, you write A kernel phi alpha, and now it is written as B kernel phi alpha. So we have shown that alpha is what? Morphism. So alpha is morphism. So we have proved. Alpha is a morphism. Now what is left? Now we have to prove that image alpha is equal to image phi, correct? Once you have to prove image alpha is equal to image phi, what you do? You take element here and prove that it goes here, and also in converse way. So you take T belongs to image alpha. It implies what? See, what is image alpha? Image alpha means here. You are taking in the image alpha. It means there exists. It implies there exists a kernel phi. It implies there exists a kernel phi belonging to S pi kernel phi, such that T is equal to a kernel phi alpha, because alpha is a map from S by kernel phi to T. And now what is a kernel phi alpha? How it is defined? It is defined as a phi earlier. So a phi, T is equal to a phi. It implies what? It implies that T belongs to image phi. And also we can go in a reverse way, that T belongs to image phi, then T is a phi. T is a phi, it means T is equal to a kernel phi alpha, and it means that T belongs to image alpha. So in this way, these two sets becomes equal to each other. Image alpha is equal to image phi. So this is also proved. Image alpha is equal to image phi. It is proved. So image alpha is equal to image phi. Now what is last thing is that we have to prove this diagram commutes. I already explained what we have to prove in order to prove that this diagram commute. We have to prove that a kernel phi natural alpha is equal to a phi. Now let's start. See, you start from the left hand side. A kernel phi natural alpha is equal to, first we operate a kernel phi natural into alpha, correct? This is what, as I already told, what is the way, that is, it is what A kernel phi alpha, and it is what, it is A phi. This we have to prove, it is done. How this is equal to this? Understand, as I already told that rho natural is from S to S by rho, and how it is defined, A rho natural is defined as A rho. Now replace rho by kernel phi here, you see same thing we get. A kernel phi natural is A kernel phi, and now it is equal to A phi. So we have proved what we need to prove. So in this way, this whole theorem is proved. Now we do next theorems, that is theorem 1.5.3. Theorem 1.5.3, page number 24. Let rho be a congruence on a semigroup S. And let phi from S to T be a morphism such that rho is contained in kernel phi then there is a unique morphism beta from S by rho to T such that image beta is equal to image phi, and such that the diagram commutes, and such that diagram commutes. Where is the diagram? Diagram is here, that is S from T, that is phi, and it is S by rho, that is rho natural, and now it is from beta. So diagram commute means, well, that is we have to prove that is rho natural beta is equal to what? Phi. We have to prove A rho natural is equal to A phi for every A belongs to S. We have to prove this. Correct? So now first thing to understand the problem. So rho is a congruence on semigroup S given, phi from S to T be a morphism, it is given, and rho is contained in kernel phi. Also remember kernel phi is also a congruence here because phi is what? Morphism, correct? And rho is contained in kernel phi, correct? Now what we have to prove? We have to prove there is a unique morphism from beta from S by rho to T such that image beta is equal to image phi, and such that the diagram commutes. So first what we have to do? We have to define a map from here to here, correct? We have to define a map, and after defining map, we have to prove that this map is a morphism, isn't it? And uniqueness will be, of course, it follows from as the diagram commutes. So uniqueness follows from here. So there's nothing to. We'll focus first on proving morphism here. So define proof. define beta from S by rho to T by A rho beta is equal to A phi. Well, first we have to check that this map is well defined or not. You see, beta is well defined. See, let A rho is equal to what? B rho. It implies that A comma B belongs to rho, correct? And rho is contained in where? Kernel phi. So it implies that A phi is equal to what? Because A comma B goes in kernel phi, it means that A phi is equal to what? B phi. It means map is what? Well defined. So beta is well defined, correct? Now what we have to prove? We have to prove that beta is morphism. Beta is morphism. Beta is morphism. That is homomorphism. So you take for any A rho comma B rho belongs to S by rho, A rho into B rho beta is equal to what? AB rho beta, correct? Why? Because rho is a congruence. So AB rho beta. Now AB rho beta can be written as we have defined, that is AB phi. Now AB phi and phi is what? Phi is what? Phi is a morphism. So A phi into B phi. Now again we can write A phi as A rho beta, and B phi can be written as B rho beta. So in this way it is proved that beta is what? So beta is what? Morphism. So we have proved that beta is a morphism, correct? Now what we have to prove? We have to prove that image beta is equal to image phi. So see how we prove it. Take T belongs to image beta, correct? It implies that implies what? When T belongs to image beta, it implies that there exists A rho belongs to S by rho such that A rho such that T is equal to what? A rho beta. And what is A rho beta? That is A phi. So T is equal to A phi. It implies that T belongs to image phi, correct? So in this way both are equal, both sets are equal. So image beta is equal to image phi. So we are done. Now what we have to prove? Finally we have to prove that the diagram commutes. Now you start from the left hand side. A rho natural beta, it means A rho natural into beta. A rho natural means A rho into beta. A rho beta means A phi. So in this way diagram commutes. And also uniqueness of beta follows from commutativity of the diagram. Why? It's very trivial, and I left as an exercise for all of you. So you can just write in the last, uniqueness of beta follows from commutativity of diagram. Correct. So now we move to the last result of my lecture, and very important result in the sense because it includes both theorems. Theorem 1.5.4. Let rho comma sigma be congruences on a semigroups be congruences on semigroup S such that rho is contained in sigma, correct? Then rho by sigma is equal to x rho comma y rho belonging to S by rho cross S by rho such that x comma y belonging to rho is congruence on S by rho, and S by rho by sigma by rho is isomorphic to S by sigma. So it's not very easy problem because it requires involvement of previous two theorems. So basically what we have to prove just is only given that rho and sigma be congruent on semigroups. If this question is asked in the long type question, so you have to prove previous two theorems, and then you will use these previous two theorems to prove this theorem, correct? And if it is asked in the short type question, then just you have to mention the statements of first two, and you have to use to prove. You have to prove this by using those two statements only. Now let's see how we prove it. So it's given just only rho sigma congruences where rho is contained in sigma, and you have to prove that this is as you have to prove that rho by sigma is what you have to prove that it is defined like that. You have to prove that this relation on S by rho, is a congruence on S by rho. You have to prove this, correct? And you have to prove that S by rho by sigma by rho is isomorphic to S by sigma. These things we have to prove, correct? So to prove this, remember, you just think like this: S by sigma, and here it is S by rho.